Hi, everybody. We're going to go ahead. We're gonna look at the what is called the ratio test in this video. This is a pretty good one. In a lot of cases, this is one of the easiest tests to perform once you understand how it works. So let's go ahead. I'm going to state the ratio test, and then we'll do a few examples so that we can see how we're going to use this thing. All right, so my ratio test is as follows. Ratio test. So we've got some series, and so we'll look at the ratio of its terms. So there's three situations. If the limit as n goes to infinity of the absolute value a to the n plus 1 over a to the n is equal to L, some number. If that number is less than 1, then the series, the sum of a sub n, is absolutely convergent. And recall, that means it's therefore convergent, right? So we technically learn that the absolute value of this series with absolute value is convergent, but that implies that this series is convergent, which is, right, we're going to be looking at a series and hoping to prove that it converges or doesn't converge. If the limit as n goes to infinity equals L, which is a number greater than 1 or infinity, right? So any number greater than 1 or an infinite limit, then the series diverges. And if the limit as n goes to infinity of this ratio of the absolute value of our terms is equal to 1, we know nothing. Then the test is inconclusive, right? Meaning, if you perform this test and you get 1, you have to go to a different test because it's inconclusive. You could have a series whose limit is 1 that diverges. You could have a series whose limit is 1 that converges. In fact, let's start with a couple of those. So I'm going to look at two tests that we already know their convergence. Let's look at the series 1 over n. Okay. So let's look at the limit as n goes to infinity, a to the n plus 1 over a to the n. This is the limit as n goes to infinity. So the n plus 1th term is 1 over n plus 1. The nth term is 1 over n. This becomes the limit as n goes to infinity. Just doing a little bit of algebra, we have n over n plus 1. And this limit is just 1, right? The limit is n over n plus 1 goes to infinity. The absolute value doesn't change anything here. These are positive numbers anyways, right? But this is the harmonic series, and we know that this actually diverges. So this is an inconclusive case. 1 doesn't tell us anything. In a similar way, if I consider the series 1 over n squared, which we know converges, it's a p series with p greater than 1, I can look at the limit as n goes to infinity of the n plus 1th over the nth term. This is the limit as n goes to infinity. The n plus 1th term is going to look like 1 over n plus 1 squared over the nth term. All of this in absolute value. Again, in this case, it doesn't matter. Everything here is positive. This becomes, again, just doing a little bit of algebra. This becomes n squared over n squared plus, over n plus 1 squared. And this also has a limit of 1, right? You can multiply that out. It's polynomials, a rational function with the same leading coefficients. So this is just to show us that these are two cases where this test didn't tell us anything, right? And so if we were presented with these and decided to try the ratio test and got this, we would have to go to something else, right? And then both of them, we can see their convergence from the P-series test. But I just want to make sure we understand that this doesn't tell us anything. So let's take a look at another series. Let's look at n equals 1 to infinity of 2 to the n over n plus 1 factorial. Okay. So let's do a little bit of work. Right? We want to test this for convergence or divergence if we can. So we need to do a few things. First of all, I want to remind us of what the factorial is, right? It may have been a while since you've seen that. So something like, let's just do it up here, right? 5 factorial just means 5 times 4 times 3 times 2 times 1. 7 let's just do 3 factorial just means 3 times 2 times 1, right? So for our purposes, we're just taking integers. The factorial is going to be the product of that integer and all the positive integers below it, okay? Now, this is a function you haven't seen a lot of, and it might seem funny that it's showing up all of a sudden. It's about to become crucial for us. It's something we're going to do use quite often in the coming days. So we're going to start discovering a few ideas about it here. So let's write out a couple of things. So I want to use that ratio test. So I'm going to look at the ratio of a to the n plus 1. So that term would be 2 to the n plus 1 over n plus 1 plus 1. So we'll have n plus 2 factorial. A to the n, of course, is just 2 to the n over n plus 1 factorial. So the ratio of these two things, right, is this one, 2 to the n plus 1 over n plus 2 factorial, divided by this one. I'm going to just multiply by the reciprocal since these are such big, ugly expressions. And then let's do a little bit of algebra. Just multiplying across and rearranging some things. We get this expression. Okay. Now, let's notice we've got n plus 1 factors of 2 and n factors of 2. There's one more factor of 2 on top, right? So we could cancel all of them out except for 1. Or another way to just think about it is using the rules of exponents. N plus 1 minus n, we get 1. So we have a factor of 2 in the numerator. Let's just write that for now. Now, let's think about this thing for a second. Let's come back to these examples we have over here. If I had something, let's do one more example. Let me put 4 factorial in here. 4 times 3 times 2 times 1. Right? Let's look at 5 factorial over 4 factorial. Right? Well, it's clear what's going to happen. Everything is going to cancel except for that 5. Right? Or in the case that we have down here, we have it reversed. The larger one is in the bottom, right? So whatever two integers these are, this is one integer bigger. So if this was 6 and 5, this would be 6 times 5 times 4 times 3 times 2 times 1, and this would be 5 times 4 times 3 times 2 times 1. Everything would be canceled except for the term, the largest term here. In other words, n plus 1 factorial over n plus 2 factorial is just n plus 2 in the denominator. Okay. If you're not clear on that, start plugging in some values for n and seeing what happens. Write out the expressions for each of them and see what happens. But in any event, this is the ratio of these two, of the nth plus 1 and the nth terms of our series, right? And of course, we're going to want to look at the absolute value, but in this case, everything's positive, so the absolute value is just the expression itself. So now we take the limit as n goes to infinity, which is just the limit as n goes to infinity of 2 over n plus 2. And I get, right, this is a pretty straightforward one. The denominator grows infinitely large. This becomes infinitely small. In other words, the limit is 0. So we are in this first case. The limit of the ratio of our terms, of our successive terms in absolute value, is equal to a number L. In this case, our number is 0, which is clearly less than 1. So this series, our series, is absolutely convergent and therefore convergent, right? So we can say, therefore, the series n equals 1 to infinity, 2 to the n over n plus 1 factorial converges. Okay? And that's an example of the ratio test. All right. All right, let's do one more before we go, and I'm gonna add a little wrinkle to this one. We're starting to get prepped for what's coming next. Maybe I'll just mention one more thing. This ratio test, a lot of times it just comes down to some algebra in here, so you can get a nice expression, and then the limits are often pretty straightforward. So it's a nice test that we have. Okay, let's do one more, and the wrinkle is going to be this. Here's the series I want to take a look at. N equals 1 to infinity of x minus 3 to the n over n. Okay. So we haven't really seen too much like this yet, but think about what I'm saying here, right? If for instance, well, here's a good example, right? We had a series. We're kind of, I hope, becoming comfortable with this idea that this is a sum. We put in values for n, and it becomes this infinite sum. We've got an infinite sum here, and if we put in values for x, we'll get very similar kinds of things. For instance, when x equals 5, we get almost the same sum that we have here. This has a little slightly different indexing. This n is, instead of an n plus 1 factorial, is just an n. But it's a very similar kind of looking thing. So we can put values in for x, and we get different series out of it. Okay. So let's see what happens with the ratio test when we look at this kind of a series that has a value for x in it, and see how that plays out. So I want to see if this series converges. So I'm going to look at a to the n plus 1. This is going to be x minus 3 to the n plus 1 over n plus 1. A to the n is x minus 3 to the n over n. A to the n plus 1 over a to the n is going to be, again, I'm going to take this term here, or this factor here, x minus 3 to the n plus 1 over n plus 1, and I'm just instead of dividing by this, I'm multiplying by the reciprocal. It makes it easier to write out. Let's do some algebra. So I'll have an x minus 3 to the n plus 1 over an x minus 3 to the n. There's one more factor of x minus 3 up here than there is down there. So everything will cancel except for one factor. So I'm going to have x minus 3, just a single factor of it. And then I've got n over n plus 1. Okay, so I just kind of did some algebra, canceled some things, and then just put this to the front since they're kind of two separate kinds of expression. Let's finally put absolute value around this whole thing. and then we'll use some rules for absolute value. This can be the absolute value of x minus 3 times the absolute value of n over n plus 1, which is the absolute value of x minus 3 times n over n plus 1. I can drop the absolute value for that second expression because this is always positive. Okay, I can't drop it here because depending on the values of x, this could be negative, right? So I can't really drop the absolute value there. So now let's perform our test. So we're going to take the limit as n goes to infinity, a to the n plus 1 over a to the n is equal to the limit as n goes to infinity. Let's just put in the expression we have here, the absolute value of x minus 3 times n over n plus 1. All right. X minus 3 is a constant as far as n is concerned. Changing n doesn't change the value of x minus 3. So this is a constant in terms as far as this limit's concerned. I can slide it forward. And then we'll have the limit as n goes to infinity of n over n plus 1. Now the limit as n goes to infinity of n over n plus 1 is just 1. Right? Rational functions, leading coefficients, same degree, leading coefficients are both 1, so this is just 1, which means our limit is just the absolute value of x minus 3. Right? So let's look back for a second. Right? Here's our ratio test. Our series will converge if this limit is less than 1. It will diverge if the limit's greater than 1, and we don't know what happens when it is 1. So let's just translate that to what our limit is. Our limit is x minus 3. This series converges if the absolute value of x minus 3 is less than 1, which is equivalent to saying x minus 3 is between 1 and negative 1. I can add 3 to everything, and I get, in other words, it converges if x is between 2 and 4. So this series, if I put in values for x between 2 and 4, converges. Okay. Now, let's think about what else we have. We have it diverging if the limit is greater than 1, so we would diverge for x less than 2 or x greater than 4. These are going to be the values where this limit is greater than 1. What we don't know is what happens when x is equal to 1. Or sorry, this absolute value is equal to 1, which is what happens when x is equal to 4 or equal to 2. Our test doesn't tell us what happens at those endpoints, right? Remember, the test is inconclusive. However, let's take a quick look at those endpoints. When x equals 2, the series is, well, if I put in a 2 for x, I get 2 minus 3 is negative 1 to the n over n. We've looked at this series before. This converges by the alternating series test. So I'll just write which converges. When x equals 4, the series is n equals 1 to infinity. I put in 4, I get 4 minus 3 is 1 to the n. 1 to the n is just 1, is just 1 over n. This is the harmonic series which diverges. Right? So let's pull this all together. The series, the sum is n equals 1 to infinity of x minus 3 to the n over n converges for, well, what do we know? It converges when x equals 2. That's what we showed here. We already knew it converged for greater than 2, so it's greater than or equal to, and up to 4, but not including 4. So now we have this interesting thing where not only can we prove convergence, if we have series with variables in them, we can sometimes get convergence over certain regions, okay? And this is something that we're going to do a whole lot of in the chapters after this one, but I wanted to give a little introduction to it here. Okay, that's it for this one. We'll do some more examples of these later on. All right, I'll see you next time.